You will probably find the title of this class a little bit strange in the sense that it combines something very familiar to you, namely areas. I'm sure you have seen and have talked and have computed areas since very early in your schooling, and the name of some person that you probably have never heard of before. Well, we're certainly going to talk about areas, and we'll be talking about these fellows' sums, and we're going to see what they have to do with each other. But first of all, let me introduce you what this character is. His name is Bernhard Riemann, and once again, he's one great name in mathematics. Is one of the people who has done a lot of work on, especially the theory of integration, trying to clarify what integrals are all about and which functions are integrable and all these kind of things. Notice that Riemann lived about 200 years after Newton, so at that time calculus was still being developed very strongly, and it still is to some extent these days. So you're talking about a live area of mathematics, not a dead one that goes back to 400 years. But the contributions of Riemann are really not going to touch us yet in this course, so we're going to leave him behind. Just glad that we've made his acquaintance. Let's go back to what you're familiar with, areas. Well, if I ask you what the area of a rectangle is, then you will certainly know that the area of a rectangle is obtained by measuring its base and measuring its height, or if you want the length and width, and then multiplying that together. I'm not sure if you're aware of the fact that there is no proof required for this. This is the definition. By definition, the area of a rectangle is that much, and then we start from that to figure out everything else. So all our other area formulas need to be proved. This one doesn't need to be. Otherwise, we would not have a starting point. First of all, we have to define what we mean by area. Well, this is what it is. For the area of a rectangle, the definition is base times height. Well, once we start from that, it's very easy to go on very quickly. For instance, the area of a square is obviously b squared, right? Because in a square, base and height are the same. They both have the same length, say b, and so that's going to be equal to b squared. How about the area of a triangle? I hope and pray that you guys still remember the formula for the area of a triangle. Do you remember how to prove it? Because again, this one needs to be proved. The proof is very simple. Start from a triangle, label its base, draw its height, and simply notice that if I draw some segments in the right place, then this shows that the triangle is actually half, or the area of the triangle is half of that of the rectangle with the same base and the same height. Therefore, the area of a triangle is given by the familiar formula 1/2 base times height. And then we could go on forever and a day. I'm going to just show you a couple of more because they are of particular relevance, but you may want to ask yourself, how do we get formula for other areas of other particular regions? Here is another example of a shape that should be quite familiar to you. So the area of a trapezoid. Remember, a trapezoid is a quadrilateral that has two parallel sides. How do we compute its area? Well, first of all, we label the top base as lowercase b, the long base as uppercase b, and then we draw the height. And then all we need to do is draw one of the diagonals. And notice that this diagonal splits the trapezoid into two triangles. The triangle on the left has area little b and height h, so its area is little b h over 2. The triangle on the right has the same formula except its base is big B. So the area of the whole trapezoid is going to be little b h over 2 plus big B h over 2. Or if you factor the h over 2 out, you end up with what should be a familiar formula, big base plus small base all times h divided by 2. That's the area of a trapezoid. And again, I do hope that you're going to memorize this formula if you haven't done so yet, because it is a fairly basic and fairly important formula in geometry. Now we can continue with this kind of idea of splitting pieces, splitting a region into triangles, as long as we have what we call a polygonal region. What does that mean? A polygonal region is a region whose boundary is made up of finite straight segments, and a finite number of finite straight segments. Of course, if you have a region like this, what we can do is simply split it up again, just like we've done so far, into a whole bunch of triangles, and there may be more than one way to do that. but here is one possible way. And then now we have a whole bunch of triangles. So all we need to do is compute the area of each of those triangles, and we know the formula for each of those. All we have to do is a bit of patience and a ruler to figure out the base and the height of each of them. And then once we're done with that, all we need to do is add them all up. Here is something else that probably you're familiar with, and that's that big Greek symbol, that Greek capital sigma, that in mathematics always means a sum. So we're going to use this symbol quite a bit. Mostly as a notation. There is all kinds of mathematics that you can do with that. And your textbooks does have a lot of formula related to this particular area of mathematics where we study the properties of these summations, but we're not going to go into that. Our interest for now is going to be somewhere else. Later in the course, when we're going to look at infinite series, we'll come back to this notation and look at some of its details a little bit more in depth.